All right, how's everybody doing? Welcome back to Math for Healthcare video lecture series, and we're going to continue on with some probability or introduction to probability. Last time we saw this formula here, all right, and, where S is a sample space, so it's a set, and an event E is a subset of S. The probability of E occurring is the size of the set E divided by the size of the set S. And we saw how that gives us this basic bounds on any probability for anything. The probability is always between 0 and 1 inclusive. It cannot be more than 1. And so when you're doing problems, sometimes you get a calculation wrong, comes out something more than 1 or a number, and you should know that, well, I'm looking for a probability, so it better be between 0 and 1. All right, let's see here. Given a single fair die is rolled, what is the probability the die shows an even number? All right. So we know from our previous problems, and maybe I'll just go over it again, the sample space here is the set containing 1, 2, 3, 4, 5, 6. All that we could get on a 6-sided die. What is the event we're interested in? That is an even number. That's 2, 4, 6. That's it. And so the probability of E equals 3, 6, which can reduce to 1/2, which we would expect. Okay. If a fair coin is tossed 3 times, what is the probability of exactly 2 heads showing? So, refer to your book or go back to the previous slides to see that the size of our sample space is 8 here. I don't want to list them all, but remember there was the tree diagram that we did to look at that. And what was the probability of exactly 2 heads showing? Well, our event E of 2 heads, if you remember, was we could get 2 heads and then a tails, a heads, a tails, and then a heads, or a tails and then 2 heads. So that the probability of exactly 2 heads showing is equal to 3/8. Single playing card is drawn at random. What is the probability of drawing a face card? Well, I advise you to look in your books. You'll find what's in a deck of cards, but maybe I'll go over quickly here. There's 52 cards in a deck, and then there's 13 ranks. Okay, what do I mean by that? Well, we got aces, 2, 3, 10, jack, queen, king. Those are our ranks, and we have 4 suits. Those are clubs, diamonds, hearts, and spades. Okay. Notice, what does this mean? 4 times 13 has to be 52. But that's the basic. So here, our sample space is all the possible 52 cards. So the size of our sample space is 52. All right. The size of our sample space is 52. What is the probability of drawing a face card? The face card, the ranks are, let's say E is the event of getting a face card. Our ranks of face cards are this jack, queen, and king. They're the things that have a face on them. All right. And there's 4 of each of those for a total of 12 cards. And so the probability E is equal to 12 50-seconds. And if we want to see that next, what it is in decimal, 12 divided by 52, enter about 0.231 comes out to be. Good. All right. Now, there's also empirical probabilities, where we don't. It's more out there in the real world. For instance, in this problem, right, we got in 2008, funding for research and development in the United States totaled $397.6 billion. Support came from various sources, as shown in this table. What is the probability that the funds for a particular project came from the federal government? Well, what do we got? We have the size, let's say, the size of our sample space. What is that going to be here? What does it actually contain? What it actually contains is every one of these $397.6 billion. So the size of it is 397.6. Remember that 0.6, it's billions, so it's not like a half of a dollar or something like that. 397.6 billion is the size of our. And then what are we asked about? Particular fund came from the federal government. Let's call that set F. We need to know the size of F, and that is 103.7 billion. So that tells me probability of F equals 103.7 over 397.6. Yes, both are in billions, but those things cancel out. And so we're looking at somewhere close to a quarter, right? But let's see what that is specifically. Let's see, 103.7 divided by 7.6. Looks like that's approximately 20.261. Okay. Now, let's say a single card is drawn for an ordinary deck of cards. Find the probability that it will be a red card or a face card. So there's a couple ways we could go about this. Is the first one maybe, let's just figure out how would we do it. Well, we know there's 12 face cards. Face cards. And how many red ones? 26. Half of them are red. I didn't go over this before. Half of the hearts and the diamonds are both red cards, and any spade or club is going to be a black card. So we got 26 red cards in a deck. All right. Now, we can't just add them together, right? 12 plus 26 to get the size. By the way, we still have our sample space here is still 52. What's the problem? Well, there's some face cards that are red cards, and in fact, there's 6 of them. So, let's say getting a red card is R, red card, and a face card is F, face, and we see this is equal to 32, which is equal to the size of R union F. Right? Oh, and that's just like our union rule, and in fact it turns out to be the same, and so that tells me the probability of R union F, let me say this, is equal to 32 out of 52. Now, just like our union rule, we could have used that as well. So we could get the probability of R union F equals the probability of R, as long as we have these equally likely outcomes, plus the probability of F minus the probability of their intersection. That comes straight from the union rule for counting the size of sets. And this turns out to be 12 out of 52 plus 26 out of 52 minus 6 out of 52. And we end up with 32 out of 52. And just to get an idea what that decimal is, 32 out of 52 is about 0.62. And that's our next rule here. Union rule for probabilities is the same as the union rule for counting, as long as our sets have our sample space is made up of equally likely outcomes. Okay. Suppose 2 fair dice are rolled. Find the probability at least 1 2 is rolled. So here we need to find the sample space, and this is a little tricky. All right. Just like with the coins, in order to get equally likely outcomes, we're going to kind of put an ordering on dice, even though we don't really think of that. In other words, we're going to have the first dice and the second dice, or the blue dice and the red dice, whatever you want to think about it as. And we're going to see for dice problems, there's 6 possibilities for the first, 6 for the second, and we get the size of the sample space is 36. Now, let's go and visualize this. This is your sample space. You'll find it. So here it's broken up red die and green die. All right, and we're finding at least 1 2 is rolled. Okay. E be the event, at least 1 2 is rolled. Okay. So here we saw, well, I wrote it down before, but notice, well, the first die has 6 possibilities, second die has 6. You could visualize it as a 6 by 6 square. And so we know the size of our sample space is 36. And we need to find the size of our event E here. Okay, at least 1 2 is rolled. Just so you know, that's clear, at least 1 2. But in general, when they say 1 2 is rolled, they mean 1 or 2. But they mean at least 1, like I do here. Notice, where do we have that a 2 shows up? Is we have this whole column, right? In this whole row. Notice, though, we would count these double 2s twice. So instead of 12, the size of E is 11. And thus, we get the probability of at least 1 2 is rolled is 1136. Which, by the way, that's going to be the same for every number. They don't change. Right? It's going to be the same thing for, say, I don't know, at least 1 4, right? There you're going to have, and it's going to double up there. You're going to have 11 of them. 1 die shows a 2. And the sum is even. Let's go back to our sample space. We still got the same size sample space. Okay. And we want to look at, let's see here. 1 die shows a 2 and the sum is even. Alright, so let's rewrite those. We'll say E is the event. One die shows and add at least here. At least 1 die shows a 2. And we'll let F be the event. What do we need here? The sum is even. And what they're asking us to find, right, is the probability of E intersect F, because it's and. And so let's see here. We got E, at least 1 2. That looks, it's all in this section. And then F, the sum is even. Alright, I want you to look at this a little bit, but we could see the sums are going to be on our diagonals. So this sum is 2, right? 1 1. That's going to be a sum 2. So that's even, right? Then the next diagonal, so we'll do this, that's in there, or in our F. Next diagonal is 3s, that is not even. The next diagonal is 4s, that is even. And then the next diagonal is 5, and then 6. Notice 7 is the long one. And then 8, we go back behind the diagonal. And then 10 and 12. And now we want the intersection, right? So we only want those red slashes that are inside the blue. So that looks like we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So the probability is 5 out of 36. Okay. Oh, yeah. The sum is 11, or one die is a 5. Now, we could use our union rule, or we could use our sample space. And I advise printing out these things so you could switch them in. All right, so what are our two sets that we have? Still the same sample space, still 2 fair die. Okay. So, oops, went the wrong way there. The sum is 11, or one die is a 5. Okay, so let's let E be 5 and F be sum is 11. Oh boy. Now, where do these show up? All right. E will do in blue. Let's see, 1 is a 5. That's going to be this row and this column, notice, right? F, the sum is 11. Let's see, those were on the diagonals, correct? The green, the sum is 11. That's these two. Oh, and the size of their intercept. Oh, what are we looking for? Let me go back here. Sorry. Or one of the die is a 5. Okay? So we just want to count these up. And notice this, we're going to get 11. Double check that, but we get that the probability of E union F equals 11 out of 36. Okay? So that 1 is a 5, or the sum is 11. It's 11 out of 36. Why? Because 5s are on both 11s. That's why it doesn't change from the number of 5s. The sum is not 5. Okay. Well, we could go back to our sample space and we could go ahead and find all the sums are not 5. All right, let's see here. Well, let's... When I start doing this and I realize I'm going to cross everything out besides that. So that's going to be, let's see here, what? 36 minus the 1, 2, 3, 4 that are in there. So 32. The probability... let's say, E equals not a 5. So that is what I want, right? The sum is not 5. Well, those are all the red ones, and we could see that the probability of E is 1, 2, 3, 4, 4 out of 36. Notice this. Oh, sorry. I did the opposite. We're going to use that in a second. No, not a 5. That's all the reds. So that's 32 out of 36 of them, right? Yeah, so that's going to be 32 out of 36. Notice we could have also done 1 minus the probability that the sum is 5, which is its complement. So 32 over 36, we get the same thing. This is what we call the complement rule. Very useful, and of course it goes the other way. Probability of E complement equals 1 minus the probability of E. And maybe last thing I'll say with that is that also tells us that the probability of E complement plus the probability of E equals 1. Okay. All right, so I think we'll stop there. And we got one more video ahead of us for probability, for introduction to probability at least. And then we move on to independent events and conditional probabilities. Once again, please let me know if you have any questions. And don't forget to work on some problems as you go through these videos. All right, have a great day.